Gnanam paramam dheyam. Knowledge is supreme.
The second part we can call, this is the name of the module we are going to discuss now. Snapshots of bond breaking. Now this is not a name that I thought up, this is the name that Ahmed Zuhail had given to his experiments, and I think it was motivated by this. You must have seen, right? Somebody many years ago had a couple of people had argued about how does a horse run. When a horse runs, is it ever that all the four hooves are off the ground? That was the bet. And to understand that time there was no movie camera or anything. To understand that, the experiment that was done is that many cameras were set up one after the other, and the shutters of the cameras were attached to some string, and the horse was made to run so that in every step it would break a string and a photograph would be taken. So that was a high resolution spectroscopy in the day, high resolution photography well, many years ago, when all this electronics was not there. And I am sure all of you have seen those photographs of that horse running in different phases, and that tells you whether, I will not tell you whether all the four hooves come off the ground at the same time or not. You need to search and see. But those snapshots have actually been the motivation of many things, starting from your movies to trying to understand how a very fast process takes place. So Ahmed Zuhail called his experiment snapshots of bond breaking, and the first experiment we will discuss is photodissociation of ICN. Okay? That is a simple pump probe measurement. By the way, this photodissociation of ICN, I don't know why I have not written it here, is discussed in Macquarie and Simon's book. It is enough if you read this part from Macquarie and Simon's book. Now, in this experiment, there is a small modification from what we had discussed here. Here we had talked about absorbance, right? In Ahmed Zuhail's experiment on ICN, he did not monitor absorbance. Rather, he had monitored fluorescence. This is how the experiment was. These are the two potential energy surfaces of ICN. Okay, if you have studied a course on chemical bonding, you would know very well what these potential energy surfaces mean. So they look very much like your bonding and anti-bonding, right? But let us just say for now that this is a potential energy surface where, yes, of course it is bonding, and this is a dissociative surface, right? There is no minimum in the upper surface. So these are the two lowest energy potential energy surfaces in ICN. That was known already from calculation. Now, until yesterday we were talking about 1917, right? Einstein's paper was in 1970, 101 years ago. Now we have moved forward to 1980s. So there is a huge jump in time. So by that time all these quantum chemical calculations and all were done. So, and Ahmed Zuhail knew that this is what the potential energy surface is supposed to look like. So what it did is, he used a pump which was UV, 306 nanometer. Okay, that took the system from the one with a minimum to the dissociative surface. Okay, the moment it goes to dissociative surface, what happens is you get the product I plus Cn. We need not worry about what is this chi doublet sigma plus is for the moment, but by the time we are done with the course, we will know what it means. Okay, let us just understand that when it goes here, then the molecule goes to, so this IC bond dissociates. Okay, so this is an efficient way of breaking a bond. And remember what we are trying to do? We are trying to find out how much time it takes to dissociate a bond. That is the fastest possible chemical process. The way it was done is this: you go here, then you get I plus Cn, right? Cn is a product. It was also known that if you use 388 nanometer, then Cn goes to an excited state which is emissive. So, this emission was actually monitored as a function of time. Same pump probe experiment, pump on one side, intense pump, feeble probe. So, what is the wavelength of pump? 306 nanometer. What does it do? It takes the molecule to the dissociative potential energy surfaces, as a result of which IC bond breaks. Where is the probe? Probe wavelength was 388 nanometer, right? And that was not monitored. That is the only additional thing. What was monitored was the emission. Okay, so emission was monitored. This emission is called laser induced fluorescence that we had talked about very briefly yesterday. Okay. Now, when I look at this plot of laser induced fluorescence intensity against time, what kind of a plot do I expect to see? So, this is exactly like this, state 3, right? ICN, ground state, promote to this locally excited state of ICN, immediately it crosses over to I plus Cn. I should not say immediately because we will talk about some time there. So, it crosses over to I plus Cn. Now, we are monitoring the population of Cn. How will the population of Cn evolve with time? Like this or like this? Yeah? Like this or like this? When you do the pumping, does Cn get populated? No, right? What gets populated is the excited state of ICN. Where does Cn come from? As a result of breakage of IC bond. Okay? So, Cn is like this. So, what is the time evolution of this state 3? This, isn't it? So, you should see a rise in the initial time, eventually it will decay. And this is the experimental result. See a rise? What does this plot mean? Well, minus 400 means what? The pump has arrived, the probe has arrived before pump. As I told you, time 0 means the time of arrival of the pump pulse, right? Initially, what you have is ICN, IC bond is intact. Now, at time 0 also more or less it is intact. Then, as time passes, the concentration of Cn increases, and finally, it looks like it has reached saturation. Actually, it is not saturation. You go to much longer times, it is going to decay also, but that is not of our interest. Our interest is how much time does it take to go from the dissociated state to, the undissociated state to the dissociated state. That is what we get by curve fitting to an exponential growth, and the time that you get is 205 femtosecond. The error is plus minus 30. If you remember what we had said yesterday and in the beginning of the previous module, we had said that from Eyring equation, the fastest chemical process, that is breakage of a bond, should take about 170 femtosecond. That is the expectation from theory. And this in front of you is the experiment that actually showed that the time involved is more or less what you get from Eyring equation. Alright. So, this was the first report of measurement of time of bond breaking, and the only way you could do it was by using the speed of light, that is spectroscopy. Okay. And since that was so fundamental, it is no surprise that this is what got Professor Zuel his Nobel Prize in 1999. Are we, no, any question? Any question on this experiment, or have we understood completely? Manthan says the intensity that we are measuring is proportional to the population of which state, right? It is proportional to the population of this state, because if you remember the discussion we had towards the beginning of the course. We will keep coming back to those basics time and again. Intensity of emission is determined by which parameter? Quantum yield. What is quantum yield? Well, IM by IAPS. How did we write IAPS? I0 into 1 minus 10 to the power minus absorbance, right? and at low absorbance that actually just becomes A. Okay. So, measuring fluorescence, so more the absorbance, more the fluorescence, right. So, when I measure fluorescence of this state, indirectly I measure the absorbance of this state. Okay. If more light is absorbed by this state, then only I will get more fluorescence from here, that is all. And the reason why fluorescence was used instead of absorption is that there is a problem. So, whatever I have told you here, I have only told you the positive side of the story, I have not revealed the problematic side of this experiment. The good thing about this experiment is that it can let you see everything, anything that absorbs. The bad thing about this experiment is that it lets you see everything, anything that absorbs. The strength is actually a shortcoming as well, because the signals that you get from here, if you look at absorbance, are so very complex. Because see, what have I done here? The way I have presented this problem to you, I have kind of tricked you into thinking that this state absorbs energies that are absolutely not absorbed by this state. That is not necessarily correct. That is not usually correct. Invariably, there are regions of overlap of absorption of 1, 2, 3 and whatever other states that are there. So, this experiment is called transient absorption, right. This transient absorption data are usually very complicated and not easy to understand, alright. And here, since such a fundamental question was being addressed, and since there was a way of bypassing the problem, because this emission, if you look at emission, only this state is emissive, nothing else is. So, if you look at emission, then you end up probing only this CN and nothing else. That is why emission was used rather than absorption in this case. Manthan, are you answered? Okay. Any other question? Yes. How do I get femtosecond time resolution? Okay. Let us do a simple calculation. Suppose I want to, so if you remember, what I am doing essentially is I am changing this path length, I am playing with the path difference of pump and probe. How am I doing this? By moving these mirrors. Okay. So, by what distance do I need to move this mirror if I want resolution of 1 femtosecond? I have a position of the mirrors, this is it, okay. Well, actually it is like this, 2 mirrors, it is called a retroreflector. I move it to some distance S to get a time resolution of 1 femtosecond. How do I get it? Simple, you know what is C, right? S by T equal to C, S equal to C into T. This is 3 into 10 to the power, I will write it in centimeter, no I will write it in meter. 3 into 10 to the power 8 meters multiplied by time is 10 to the power minus 15. This is meter before I forget. This turns out to be 3 into 10 to the power 7 meter minus 7 meter. Actually, this is not right, isn't it? There is a factor of 2 as well, because if the mirror moves by S, path length that you have produced is actually 2S. So, factor of 2 will also come in. Okay, but we are not bothered about that. Let us just look at this. 10 to the power minus 17 meter means what? 0.1 micron. Right? So, I have to be able to move it by 0.1 micron. What is the easiest way of getting translational motion? Of course, I am not going to go and push it, right. I have to use gears, I have to use, essentially what is done is, this retroreflector is mounted on a long screw, okay. You turn the screw a little bit, this thing moves a little bit, okay. So, what determines time resolution essentially is the pitch of the screw. I hope we have not forgotten what the pitch of the screw means, right. What is the pitch of a screw? A screw has grooves, right. Separation between 2 grooves essentially, right. And what is the least count? The least count is actually smaller than the pitch of the screw, because you can turn it by maybe half a degree also precisely. Okay. So that way mechanically the good thing is the time resolution here depends on our ability to machine an accurate screw and use what is called a stepper motor. Do you know what step motor is? Or do you know what a motor is, right? DC motor. How does a DC motor work? You have a magnet, right? You apply potential difference and then you get circular motion. Is it continuous? Is it discrete? It is continuous, moves like this, right? That is a regular motor. But then in many devices like say your printers, how do the printers go? If the printers in the printer, if it moved continually, then it would be difficult to print, right? So in printers the movement is in steps. That is what uses what is called a step motor. I will not discuss how a step motor works, that is a little too complicated for this. So you can use a step motor, you can use an accurate screw and easily get resolution of femtoseconds. Okay, we just have to be able to move our retroreflector in a very precise manner. That is machining. Fortunately, machining is something that human beings have been at for several centuries. So we are good at that. Any other question? No? Then I will quickly discuss another experiment of Professor Zuel, which is also interesting. But before that, what are the properties of laser that have been used in the experiment we just discussed? One is monochromaticity, second is pulsed operation, third intensity, right? Because unless you have an intense pump, you cannot do this experiment at all. Intensity. So several properties of laser make it useful for this kind of experiment. Now we are going to talk about another experiment where all these properties are important in addition to one more property. What is that? A laser is a coherent source of light. Okay. Well, same group, similar experiment, but different system. System here is sodium iodide. Okay. So what we have learned so far is how much time does it take for the bond to break. Now the question we try to address takes us to a finer degree of understanding. Now, how many of you have studied this transition state theory in BSc, right? Transition state theory, remember? So in transition state theory, it's all about vibrations, right? How does the bond break? Is it that the bond is sitting there happily sleeping, all of a sudden it breaks? No, right? So what happens is there is a low frequency vibration, right? And then this vibration is the one that has to be activated until the bond breaks. So if that is the case, what I should be able to see, if I can do the right experiment, is that I should be able to see that vibration. So you understand what we are trying to say here. On all the chemistry that we have learned, we have said you cannot see the transition state. Is it right or wrong? Right? Conventional organic chemistry, inorganic chemistry, everywhere we said the transition state is something that seems to be like a figment of our imagination. The entire theory is there based on it, but how do you see a transition state? Can you actually see the oscillation? You can. This is how it is done. Now one thing I need to tell you is that when you take a femtosecond pulse, it is actually not very monochromatic. It is broadband. Why? Because if the pulse is small, say 5 femtosecond, then the uncertainty in time associated with it is also no more than 5 femtosecond, right? Very small uncertainty in time, that brings in a large uncertainty in energy, same uncertainty principle kind of argument. Okay. So since it is a broadband pulse, what it does is when it performs an excitation from an electronic level, you understand that each electronic level is associated with many vibrational levels, right? This as well as that. So actually the transition takes place from many vibrational levels to many vibrational levels. So what you have in the excited state is not one wave but many waves, and you are doing a coherent excitation. That means at 0 time, at the time of pumping, all these waves are in phase. Okay. What do you call such a collection of waves? Louder. A collection of waves, all of which are in coherence to start with. What do you call it? You add a lot of sine waves. It's a packet of wave. So wave packet, right? This is a wave packet, a collection of waves. And then I think you know that when you have many waves, what happens is initially the intensity is large, then it falls off. And if there are too many waves, they don't get back again. That is what a wave packet looks like. So this wave packet is produced. Now in sodium iodide, what happens is this. This is the potential energy surface of Na plus I minus, ionic. There is also a potential energy surface of Na plus I, sodium plus iodine. Everybody has done flame test, and there we have seen yellow color of sodium. That is not Na plus, right? That is sodium, Na, right? This is why it happens, because there is a possible, it is possible to go from this Na plus I minus potential energy surface to Na plus I, neutral potential energy surface. So what you do is you excite it, and then the wave packet oscillates between the ionic and the covalent potential energy surfaces. Can you see it? First of all, what kind of shape do I expect? If I tune my probe to that of NaI, Na plus I minus, then I expect a decay. If I tune it to that of Na, neutral, then I expect a rise, right? But if there is an oscillation between two, then what do I expect to see? The rise will not be like this, it should be something like this. That is what you get. So here what you see is, not only do you get the time required for breakage of a bond, you can actually see how it is breaking. So like that horse we talked about, whether the four hooves come off the ground at the same time or not, you can actually see this oscillation between Na plus I minus and NaI surfaces. So this low frequency vibration that is central to transition state theory, this is your low frequency vibration, and you can see the period is about 1 picosecond. Okay. This is of course complicated, so we stop here. You can read this part from Atkins' book. I do not expect you to have understood everything today. Please read, come back and ask questions. Next day we start discussing another kind of spectroscopy which has become very important only because we have lasers. And once again, all these properties, monochromaticity, intensity, coherence, everything is important for that kind of spectroscopy, and that is Raman spectroscopy. Next day we discuss Raman spectroscopy.